All right, Chem students, today we're going to talk about the processes of solvation. You need your blue notes packet and something to write with. First thing we need to talk about is the rule like dissolves like. This rule means that polar or ionic solutes will dissolve in polar solvents, and nonpolar solutes will only dissolve in nonpolar solvents. This means that the substances are miscible, and miscible sounds like mixable, if that helps. Now, like dissolves like combinations, if we have a polar solute and a polar solvent, that will work. An example is sugar in water. For ionic solutes, those also make ions. They would be easily dissolved in the like polar solvent. Example would be sodium chloride in water. Now, nonpolar solutes and nonpolar solvents. A good example of this one would be gasoline being miscible with oil. Now, note that water, which is polar, and oil, which is nonpolar, do not mix. They are immiscible or unmixable, if that helps. We can practice with problems like this with word phrases here. Benzene does not dissolve in water, but it does dissolve in carbon tetrachloride. So we need to figure out which is polar and which is nonpolar. Now, as a baseline, we always know that water is polar. Now that means that water, like we said, is polar. And if benzene does not dissolve in water, it must be nonpolar. That would mean they're immiscible. So polar water, nonpolar benzene. But if benzene does dissolve in carbon tetrachloride, we know that carbon tetrachloride must also be nonpolar. Now, glucose does not dissolve in benzene, but it does dissolve in milk. We know that benzene is nonpolar and glucose does not dissolve in it. That means they are not alike. Glucose must be polar. And it does dissolve in milk, so milk must be also polar. It's because they're alike. Like dissolves like. Oh, actually, we just covered that, so glucose is polar. Okay, our last one. Water does not dissolve in carbon tetrachloride, but it does dissolve in milk. Water, which was polar, does not dissolve in carbon tetrachloride because it's nonpolar, but it would dissolve in milk because milk is polar, and like dissolves like. Okay, so now we want to talk about how we dissolve ionic substances. This process is known as solvation. And we have a diagram of sodium chloride here dissolving in water. So the water molecules, the polar parts of the water molecules would be attracted to the ions within the sodium chloride, and that will help the sodium chloride dissolve. And we have a little video to help you see that. Okay, we have several factors that will increase the rate of how fast something dissolves. First one, increase the temperature. If you increase the temperature, you will increase how fast something dissolves. The second one, if we increase the surface area, meaning we make the particle size smaller, giving it greater surface area, it will dissolve faster. These chunks will not dissolve as fast as this powder. Now, the third and final rate that you need to know is we can increase agitation, meaning stirring or shaking something. That will also increase the rate of dissolving. Factors that affect solubility itself, meaning how much solute will dissolve. The first one is temperature. For most solid solutes, an increase in temperature will increase solubility. There is a direct relationship. If one goes up, the other one will go up. So increase the temperature, we increase the solubility of a solid. Now for gaseous solutes, an increase in temperature will decrease solubility. So it is the opposite. It is an inverse relationship. If you think about it this way, if you take a Coke and you heat it up, the carbon dioxide will rush out of there and it will go flat very quickly. Because if you increase the temperature of a liquid, a gas does not like it. It will not be soluble anymore. It will come out of solution. Now, a good tool to predict solubility is something called a solubility curve. It plots solubility versus temperature for various solutes, and we'll work on those in the next video. Now, another factor that affects solubility, meaning how much solute will dissolve, is pressure. This one only applies to gases. If we increase pressure, we will increase solubility. That's why your Coke can is pressurized. They have an increase in pressure, which will keep all of that carbon dioxide in solution. So increase the pressure, we increase solubility. We can determine this relationship with Henry's law. The solubility in the beginning divided by the pressure in the beginning will be equal to the solubility at the end divided by the pressure at the end. Now, this is a great diagram that shows that relationship. Under normal conditions, it's common for CO2 to dissolve into water. Every once in a while, a carbon dioxide molecule will penetrate the surface of the water and be in solution. Now, if we drop the temperature, the activity of the molecule slows down and the hydrogen bonds become stronger. CO2 can't break free anymore, so if it goes down into here, it's not as easy for it to come back out. If we also increase pressure, we can put more carbon dioxide into this area up here. It will keep all that carbon dioxide down in the solution, therefore increasing the solubility of the gas. Okay, let's work a couple of Henry's law problems as examples so you can understand how this works. So I'm going to label this as I go. Problem 1. The solubility of carbon dioxide gas in water is 1.713 grams per liter. That is solubility 1. And that is at 1.0 atmosphere pressure. So that's pressure 1. That's our starting point. They're asking us what is the solubility if the pressure is decreased to 0.50 atmosphere. So that's my pressure 2. So I'm looking for S2. So I'm going to start with my Henry's law formula. We provide this for you. And I'm going to cross multiply. S1 times P2 will equals P1 times S2. Then I can divide by P1 to have everything on this side of the equation. So S2 is going to equal, I plug in all the numbers from up here, and it's going to look like this. Multiply across the top, divide by the bottom. Our answer will be 0.86 grams per liter for our new solubility. Problem 2. The solubility of O2 gas in water is 0.019 grams per liter. There's solubility 1. And that is at 1.0 atmosphere pressure. That's pressure 1. What is the pressure if the solubility increases to 0.0475 grams per liter? So they're giving us the solubility 2. We're going to be looking for the new pressure, so that's pressure 2. So I start with my Henry's law here, and I rearrange it. I cross multiplied S1 times P2 equals P1 times S2. Divide by S1, so they're all on the same side. Plug in all of my numbers here, and when I multiply across the top and divide by the bottom, I get 2.5 atmosphere as my new pressure. Now, that's it for today's video. You want to work on the corresponding practice packet pages, and we'll see you next time.